Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about unique types of multimeter. So let's dive deep into it. Now first, I'm pretty sure all of you know about multimeter because it's the starting point in everyone's electronic journey. You will not find anyone who has oh, I became electronic engineer and does not know what multimeter is. So that's not happening. Now be mindful, multimeter comes in different ranges, like some dirt cheap like these puppies, I'm pretty sure, and some are bonkersly expensive. Look into Fluke ones, they are expensive. So they are very good at core things, like three core things that you can trust, even the cheapest multimeter: voltage, current and resistance. You will get these things and this will be decent enough. So that's the good point. However, while this is good and you can find modern meters that are like, this was manual ranging, so now we have auto ranging, and again this has a bit more flex, so to say. Not only it can measure resistance, voltage, it can also measure capacitance, so it does have a bit more oomph. However, this will not perform in certain domain. No matter what you do, it does not matter whether you have this sort of auto ranging or this sort of clamp meter. Fundamentally, there, or even old school analog meter, there is a fundamental limit where these meters will fall apart. Like this DMM is not designed to go there. So sometimes it will not work, no matter what you have, no matter which brand you have, because again, outside of its range, so to say. So if you have to measure very large or very small ohms resistance, while all meters do resistance and they do decently well enough, but the moment you make it very large, they will fall apart, as in like above 10 mega ohm, or very small milliohms and let alone micro ohms. Yeah, they will be like, nope, can't do that. So that's outside the dynamic range. And then other things are way too complex. For example, inductor is one of those things. You could find system that could claim, hey, I can deal with capacitor. Yeah, nobody will even dare to touch inductors. That's how messy it is. It's not that it can't be done. Of course it's done. That's why our world has inductor. It's just that it's messy AF, so to say. So there are certain scenarios where like you have to deal with this complexity, this different ecosystem. So let's dive deep into the first one, which is Milli-Ohm meter. Now, normal meter, multimeter cannot go, does not matter which brand, will generally not go below 1 ohm. Like if you go below 1 ohm, it's like, it will try to, but it will not be trustworthy. And again, it's physics problem. You cannot bypass it because generally all meters are designed for basically only 2 probes. That's not good enough. You need 4 probe wiring, basically this sort of system. Because physics has this cheat code, meaning if you're sending current through a wire is not made out of superconductor, it will have voltage drop. However, if you're measuring from something else, that will not have the current draw. So you can reach a point where because of the high impedance of a voltmeter, you can send majority, as in like 99.999% of energy through different cable, and the voltage drop will not affect your voltmeter reading. So that is fundamental necessity to have basically better signal to noise ratio. That's why whenever you go into precision instrument, they are always 4 wire measurement. It has to be. You cannot trick around. Heck, even lab power supplies, if you really want, especially if you're dealing with high currents, they're like, bro, you have to use second wires, otherwise like your multimeter on the lab power supply will say, I'm sending 5 volts and 1 amp your object. If you have a multimeter at your object, it will say, yeah, I'm only getting 4. So that's why at low enough resistance, you do need 4 pro. It becomes compulsory, not optional, compulsory. And injection test current becomes much larger. For example, these things will barely dump 1 milliamp, barely, generally microamps or something like that. So whenever you are trying to measure something very small like shunt resistor or induction, basically coil resistance of a motor or transformer or those things, yeah, that's not good enough. So you amp it up, as in you can easily start with 100 milliohms, which is exponentially larger than most meters, and go into few amps or even tens of amp, like serious amount of current. That has to be done. However, because of low demand, these things are bonkersly expensive. Even though it's necessary, there are certain fields where it is becoming more and more necessary. For example, if you are working with electric vehicle, how the heck do you know the motor coils are healthy? Because right now everybody will test the insulator. Okay, cool, awesome. What about the goddamn conductor? Is conductor healthy or not? If you're dealing with transformer, cool, awesome, like you are measuring, is the insulation intact or not? But what about the goddamn conductor? Conductor also ages. So fundamentally, is it in balance? Is it off balance? You have to measure that, and normal multimeter will not cut it. So you need these sort of meter, and holy damn, these meters are expensive. That's the first time I've seen any meter that has been respected to the same level as Fluke, and is like, it's hockey meters, and they're like, yeah, Toyota service manual, have this, Milli-Ohm meter, otherwise don't even talk about us. And they specify, like, in this sort of meter, you should be below, like, let's say 2 Milli-Ohm or micro-ohm offset from each other, each stage of. I have linked a decent video down below. So essence is, these are very important tool, but they are bonkersly expensive. This is the cheapest Indian I have seen, Indian meter, and they are still god damn expensive, like bonkersly expensive. Although this is like a full-fledged meter, it goes up to 20 kilo. I'm like, bro, if I'm that range, I have multimeter. So it's like, although it does go below, like, 200 milliohm, 20 milliohm, 2000 micro ohm. That's the whole essence of it. Like, if I'm measuring a shunt resistor, this is like, I got you. Normal multimeter, what is this thing known as shunt resistor? So high power motor windings, transformers, shunt resistors, they need this. Like, this is a tool which you may not need it, but when you need it, you need it. You need it. So this puppy has high current output. That's the first thing. Can you build this yourself? Yes. We'll talk more about that in further. Then we have the Megger, so which also called Megohmmeter meter. So this is sometimes called as insulation tester. You have to understand that conductor cares about current, insulator cares about the voltage. You have an insulator, you have conductor. Conductor is trying to push. Basically, there is, let's say, human flesh here, and insulator is in between. Insulator, like, your voltage is trying to push through it. It's like doing that. That's why your insulation becomes thicker the higher the voltage, not with current. Like, you have same wire thickness, insulation thickness for household wiring, because they are generally tested for 1000 volt. So thickness will remain the same, even though you can go from, like, let's say 18 gauge to 4 gauge. Insulation thickness will not change that much. Why? The voltage was not changed. But whenever you're talking about insulation, they do care about voltage, because that's what breaks. So, and penalty of insulation failure could be lethal and destructive. For example, imagine a failure happened where the heating element, which is AC mains power, leaks current directly into your water, and your whole water gets electrolyzed. Yeah, that's a lethal. Like, yeah, electrocution hazard, serious one. And not to mention destructive. Whenever you are talking about transformers, for not only transformers are what we classify as long lead items, they never fail what you call gently. They go kaboom. So it is something that humanity have learned the hard way. Like, this is surprisingly ancient hardware that we have to build this, and we have to make it reliable. So high voltage injection is the toolkit here. For example, Milliohm one is pushing a lot of current. This puppy is pushing a lot of voltage. Now let that be very clear. These puppies are hazardous to human. As in, if you are holding the terminal of Milli-Ohm meter, nothing will happen to you. If you are holding terminal of this, you are in danger. And I do not mean like hee ha ha danger. I mean, like, you could be kaput kind of danger. So they can start with, like, mild voltage of 500 volts and go up to kilovolts. Like, again, I do not even want to know what kind of oomph they are putting for 100 giga-ohm. So fundamentally, they are pushing a lot of voltage and measuring the leakage current. And that's how they show you giga-ohm level system. Now be mindful, giga-ohm is extreme. Unless you are dealing with, like, substation transformer, you generally do not have to deal with that. But again, they come in this sort of boxes and ludicrously expensive for that exact reason. They have the oomph, horsepower. It's like... And back in the old days where we did not have reliable batteries, they had a hand-cranked generator. You kept cranking that puppy up. So it does work. Now, thankfully, this is what we classify as non-destructive testing within limit. Meaning, if you have a motor and you want to, like, hey, is this motor healthy? Let's say a flooding event happened and or motor got flooded, and you're like, okay, let's dry it out, do everything. Before you start to spin it up, do you want to test its insulation? Of course you do, because failure to do so will destroy it. So how do you test it? You use this sort of system. It works great, but it is injecting a high, short pulse, very short pulse. That's the good part. Bad part is still a high pulse energy that you are trying to push through the insulation. So if you use too much of it, it will degrade it. For example, if you use this sort of meter that is designed for substation grade system and you forced it on a AC mains motor, it will degrade it. Now, again, one setting, nothing will happen. 100 something will happen. So these things are not used regularly. They are like, oh, flooding happened, I dried out the motor, is the healthy insulation and all that. So that sort of thing, meaning every few year in inspection you use that, because it is still high voltage. It does have a risky high voltage. Like Fluke does have some of those meters where it's like, they have a giant logo, it's like lightning. But you have to, this is Megger. And this is the one of the few things that can tell you health of the insulation, meaning transformer expands and contracts day and night time. So that has some wear and tear. On top of that, because of the loading and unloading of the transformer, it also flexes, the coil itself flexes. So over time, the insulation becomes weaker. How do you know it's weaker before it fails? This puppy will tell you, like the healthy transformer 100 gigaohm. So, replace the transformer if it drops to 10 gigaohm. So they're like, okay, if it's showing 100, cool. Started to show 70, it's like, yeah, let's put it, let's start to save money for that. Started to touch 50, yeah, place the order for a new transformer, because again, large transformer could take 2 years to come. So they're like, yeah, let's place the order. So Megger is a very important tool. Thankfully, it is available surprisingly cheaply, like not even that expensive everywhere. Like, but again, let me begin. Not everyone is designed to go to 100 megohm. You would be, most of the cheap ones are like 2 mega ohm, 10 mega ohm. Giga ohm is very expensive. Because again, giga ohm is this. Now we come to another unique puppy, which is LCR, inductance, capacitance and resistance. Like, wait a minute, isn't all multimeter can handle resistance, high resistance as it, and capacitance? Like some of the new one has capacitance. So what's the deal here? Well, here's the deal. High frequency makes these things behave differently, meaning you go from resistance to impedance, and that's the whole point. They have to work with not DC, not high voltage, not low voltage, but AC frequency signal. As in the test frequency, like the bare minimum would be 100 Hertz, 120 Hertz, 100 Hertz is for 50 Hertz systems, 120 is for 60 Hertz systems, to 1 kilohertz to 10 kilohertz. Pro grade ones are 500 kilohertz, like half gigahertz. And at that point in time, things behave differently. Why? Well, here's the deal. You are like, hey, I have this resistance. You measured it, it's reasonably 1 kilo ohm resistance. Cool, awesome. Here's the deal. How is it physically constructed? Like, does it have the coil going like this? Because it's an inductor. If you have high frequency, let's say if you are dealing at 1 kilohertz, it does not matter that much. But if it's 10 kilohertz, it will cause way too much resistance at that frequency, way too much. Like, even though it's 1 kilo ohm, it will behave like, let's just say it's 10 kilo ohm. Like, why the hell did that happen? Frequency. That's why LCR is a different category. Whenever you are dealing with something that is not base load DC, you need LCR. LCR can tell you, hey, how the heck this puppy behaves at the frequency of your choosing. For example, if you are working in kilohertz circuitry, how does that 1 kilohertz work? Working at 10 kilohertz, how does it work? So that gives you necessity for having frequency as a test current rather than DC. And LCR is built for that exact testing. And generally, they also come with that Kelvin connection, so they do not warp the system. And this thing, because of the necessity, and as our world is becoming more and more digital, more and more high frequency, it becoming necessary. So ironically, this became the cheapest. Like LCR meters are surprisingly cheap. Why? High frequency microcontroller is cheap. Like if you want kilohertz of frequency on a microcontroller, that's dirt cheap now. ESP32 goes to hundreds of kilohertz. Even megahertz is possible now. Gigahertz is still expensive, but again, you can get microcontrollers that are gigahertz spec. But that's the whole essence of it. Microcontroller became cheap enough with lower grade, not high grade, low grade LCR meter can be built and you can have it. And it is necessary, let us be very clear. That's why this thing became so ubiquitous. Once a person figured out, hey, I can take a normal 8-bit microcontroller and just have this LCR, it won't be the greatest thing ever, but it will be good enough. People just ran with that puppy. And because again, everybody needs it. SMPS, how the heck you gonna build SMPS if you do not know how your resistor works at that frequency? Like most common thing, people say, oh, I built the SMPS, but the actual efficiency is barely 60%. Where the heck energy is going? Generally something that is not designed for that frequency, or you have not tested it at that frequency. So it's a core world necessity. The moment you deal with frequency and all that, yeah, you need to have this. And they come in hyper expensive to dirt cheap. Like this is less than 1,000 rupees. And this puppy is like, yeah, get quote kind of series. Get quote. This is mid of the way. Hyper cheap, Fluke series. And yeah, you need to be Bill Gates to approach this. So this is the LCR series. And again, we had something that had a lot of current. We had something that had a lot of voltage. We have something that this has a lot of frequency. These are the three independent domain. It's unlikely you can mix all three in one. Although I can see you should be able to mix Milli-Ohm meter with a normal multimeter. I do not know why it's not done. It's like, yeah, it will cause more battery drain, but you can have rechargeable battery. So I don't get that part. Now, what about DIY? Well, here's the deal. Megger is one of those things that I will say stay away from them because they are inherently designed to pump charge. They can pump charge through your body also. So it's one of those things that is like, it is doable, but try it at your risk. Like that is not something I will recommend. However, Milliohm meter is cheap. Surprisingly cheap. Like people are building as LM317 kind of cheap. And if you're like, oh no, I want something precise, not milliamp, micro ohm level, people are also building that. And surprisingly decent one. Like decent one, like, oh, what if you have a lot of cheap resistor? Okay, put a lot of cheap resistor in parallel and then tune that resistor. I'm like, that's clever, surprisingly clever. So you can build surprisingly good one. And I mean $10, $25 kind of build, not like hundreds of dollars, like super cheap. Even in India, you can build it like, few thousand rupees. Or if you want dirt cheap and you are not going into micro ohm, you can do that with LM317. And some op amps. Like somebody figured out, it's like, hey, if you have 10x gain on that, the volt becomes the ohm. So at milli-ohm rating, you do not even need conversion. The unit is exactly that. So fundamentally, it's a really good thing, and I would urge you to, because again, more and more people need this nowadays. Again, shunt resistors are becoming, everything has it. So you kind of need it. And not that expensive. You can have like a standalone system that has its own meter, or something that like, plugs into normal meter, because again, you do need a voltmeter to read it. So this design has its own meter. Some designs are like, okay, you have this attachment for your multimeter. That's up to you. LCR meter, again, that has also become doable because of the microcontroller. Like some are going YOLO on it. It's like, hey, what if you have range switching? Because again, for inductors, you do need that. Like the whole journey of electronics of me started with this inductor testing. I've linked them down below. He had the issue. It's like, if you want to measure till millihenry, as in the inductance, these sort of things are good enough. But if you want to microhenry, like very low impedance, like a mains transformer, like big powerful transformer of, let's say, microwave primary side, yeah, most of these will just show a resistance. They're like, I can't understand this, too low. This is like, he built that specifically for that. Although, let them look at, this is not standalone. You're supposed to have an oscilloscope for this, but you can have a microcontroller that can read it also. It will require extra op amp and comparator IC. Not that expensive, but it can be done. So this is the whole essence of DIY. Like again, other than Megger, Milliohm one, people have built surprisingly good one. LCR, really good one, messy one is available. Heck, I have just completed my lab bench power supply. If you guys are interested to talk about it, like again, the schematics is made by me, and it does work. It does work. I wanted like a 0 volt to 15 volt. I got that, and no negative voltage rail. I have to tell you, like I learned so much in just making this one thing. Like, the hardest part? Figuring out a LED indicator. I have seen so many like, linear power supply, and surprisingly few of them have like, is it in constant voltage or is it in constant current? That LED. It took time, but I did figure out how to have that LED. Right now, the only thing missing is the switch LED. You can't have a normal LED on the switch, because if you turn it on, cool, 15 volt, or you have a resistor. What about its 0.5 volt? It will not turn on. Even 1 volt LED will not turn on. So I'm trying to build that. I got the proof of concept this morning working, but I think I have to make a Darlington. So even if voltage is like 0.8 volt, the LED turns off. I have to make sure the LED remains like till 0.001 volt. It should be able to turn on. Let's see. Again, I would urge you to, because here's the deal. A lot of engineers come out of schools. They're like, hey, I studied. Like, have you actually built the damn thing? Because you are limited by the tools. Tools are a limitation of your imagination. If you have good tools, you can think, what if I do? Oh, by the way, there are a lot of now shunt resistors that have Kelvin connection in the resistor. So again, these are amazing things to do. And again, nowadays it's surprisingly easy to do because of YouTube. So this was my presentation on basically unique types of meter. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra experiment. If you have really enjoyed it, click the hype button. If you didn't, I would say leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.